In this video, we're going to talk about how to create models using linear regression. And just a heads up, this is a very brief overview because this is an algebra class. I just want to introduce this topic to you. We go into much more detail in statistics or in other classes where we'll talk about linear regression or other types of regression. So first, it's important to understand what we're talking about. A regression model is essentially we're looking at our data in a scatter plot. So a scatter plot is just where we have a bunch of items that are written as ordered pairs, x comma y, and we plot them all, and then we look to see if there's a pattern. And if there's a pattern, then quite often we can write an equation, which is a model, called a model. We'll write an equation that sort of fits that data. So here, I might draw a line here that looks like it fits the data, or another linear function, or a nonlinear function. We're not going to get into details with nonlinear, but it's possible that would be like a cubic regression because it's a cubic function. You get the idea that we could write regression models for all of these, but in this class we're going to focus on linear. So you're going to have something that's either in a nice straight line, give or take, going upwards, a positive slope, or going downwards, a negative slope. So again, in this class, we're just going to look at linear regression, which means we're going to plot some points, and I'm going to show you how to do that using Desmos.com. And we're going to say, okay, it looks to be somewhat linear, so we're going to write a model of our best fit line. Our best fit line, what's really important to understand about a best fit line is that if you're doing it by hand, which you will be asked to do in ALEX in your questions this week, my equation would be different than your equation, would be different than anybody else's equation, because it's very unlikely that we would choose the exact same line because we're just going to be drawing it freehand. When we do this using a graphing utility to actually have Desmos or Excel or any of those functions, any of those programs come up with a function for you, those should all be the same. So if we're doing it by hand, they're all going to be different. And then when we do it using the utility, graphing calculator, Desmos, Excel, etc., we should all get the same answer. So I've given you a table of data, and your table of data has the number of chirps per second of the striped ground cricket in relationship to temperature in degrees Fahrenheit. And what I want to do is to plot these points to see what the pattern looks like. And so as you can see, I've already copied over that data. I did it by hand. I'll show you really quickly how I did it. I went to the plus and chose table, and that brings up a table just like this. And then I just started by adding 20, and then I tab 88.6, tab 16, tab, etc. So the tab just gets you to the next one. You can press and hold on that circle to choose different points if the lines are connected, which we don't want the lines to be connected, the color, etc. I'm going to go ahead and delete that because I already have this one done. But as you can see, if I look over here, I don't see any of my points anywhere. And that's because my x's are from, say, 14 to 20, and my y's are a lot further up because we're talking about temperature. So I'm just using I have a touch screen, but you can also, as we talked about before, click on the little wrench and change your x and y axes to make it work for you. So I'm just going to use my touch screen to zoom in to take a look at, does this look like a somewhat linear pattern? And it does. I can see in general these are going up as I go from left to right. So I'm going to use my linear regression, and we're going to do this on the next page, and we're going to determine a best fit line together, and we're going to create the equation for that line. The next thing I would do, now that I have this scatter plot, is to get a straight edge, and you'll have to bear with me because I'm on a computer and I don't have a straight edge, but you would use a straight edge on paper. And what I'm going to do is I want to draw a line that I feel represents the data. When you're drawing the line, you don't try to hit certain points or anything like that. So I would just take my pen or pencil, and that's the best I could do freehanding. That's what I feel the data is doing. So this is why I said you're not going to get the exact same line or equation as anybody else because we're all just doing the best we can. This is why people use computers to do this, which I'm going to show you how to do in just a minute. So what I'm going to do now is I'm going to look at my line that I have drawn, the one in black, and I need to find certain points on this line. I need to find 2 points so that I can use those 2 points to find a slope and write the equation, etc. And what I'm looking for is, does it go exactly through one of my data points, or does it, like what I feel to be this point right here, which looks to be 20, 91, does it go through any exact intersections? So for instance, I'm trying to find another good one. This guy right here seems to be right through an intersection of 16, that was a bad 16, 16, 79. So those are the 2 points that I chose. So if you were actually doing this at home, you maybe chose different points than I did, and that's okay. Because as we're doing this, you're going to end up with an equation that is similar to mine, but not exactly the same. So from here, we actually should know what we're doing because we've done this before. We're going to find the slope first, and the slope uses the slope formula, which is y2, 91, minus y1, 79, over x2, 20, minus x1, 16. And we're going to then use that slope and then the point slope formula and write it in slope-intercept form. So I end up with 12 on the top, 20 minus 16 is 4, and I got a slope of 3. And that was so lucky. Like, that was just really luck right there. So please don't think that you're always going to get a nice whole number. Usually you get a fraction that's completely ridiculous. So what I encourage you to do, let's say I wasn't so lucky and I got something like, 13 over 6, which is a hot mess of a fraction, then you just take that decimal out to about 3 places and use that instead. So we're going to stick with my 3 just because I happen to get super lucky and I'm going to get a nice pretty equation, but if you got an ugly equation, that's okay. When we're doing linear regression, it's okay to use decimals to 3 places because quite often that's what you're going to end up with is decimals. So just go to 3 places. Step 2, just as before, we're going to choose one of those 2 points and do point slope formula. So I'm going to take y minus, I'm feeling that 20, 91. So I'm going to do y minus 91 equals my slope of 3, x minus 20. And then I'm just going to keep going because my goal is to turn this into slope-intercept form. So basically just do the math. I have y minus 91 on the left. I distribute to get 3x minus 60. I'm going to add 91 to each side to get 3x plus 31. And that is my equation. And why is that helpful? Because then I can use that equation to make predictions. This tells me that if x were 0, that my intercept would be 31, which means if I think the temperature was 0, there would still be 31 chirps. I don't remember which one was x, which one was y. But you get the idea. We can make some predictions based on that equation. So when I did the work by hand, when I was making up my own equation, this was my function or equation, y equals 3x plus 31. I then let Desmos do all of the work for me and make the true line of best fit, which is called a least squares regression line. We're not going to get into all of that, but the least squared regression line is the best line of best fit, essentially. And as you can see, Desmos did the work for me. And if you want to do that yourself, I'm not going to take you through it live in Desmos, but all I have to do is enter in this exact equation. The y1 and the x1 tell Desmos to take your data from x1 and y1, which is the column headings on those 2 columns, The M and the B are things that Desmos will then calculate, and as you can see right down here, Desmos does the calculation. So my real equation, the true best fit line equation, and I went to 4 places. As I said before, you could go to 3, but this came from Desmos, so this is a better estimation than mine. But as you can see, these two are similar to one another. The slope I came up with was 3. Desmos came up with 3.29, so mine wasn't quite steep enough. My y-intercept was 31, theirs was 25, so theirs is better. But again, mine was a pretty good estimation, and in ALEKS, you'll be doing that yourself, finding the best estimation. Obviously, the most important thing about being able to create a best fit line, or the model for the best fit line, which is the whole purpose behind doing it, is to then to be able to make predictions, and that's what we want to do. So it's super important when you're making predictions that you remember what was X and what was Y. So as we can see, I don't have any labels on my graph, but I went back to my table to verify what was what, and the X values were cricket chirps, and the Y values were temperature. Now, why is that so important? Because when I estimate, I need to know, am I plugging in X, cricket chirps, and solving for Y, temperature, or am I plugging in Y, temperature, and solving for X, cricket chirps? So a couple of slides ago when I said, hey, we're going to make predictions, I think I had the X and Y values wrong, so I apologize for that, but I'm going to have them right here, so let's take a look. A, estimate the cricket chirps when the temperature is 75. So it tells me the temperature, and we know the temperature is Y, so I'm going to plug 75 in for Y, and then 3.2911x, x is what I'm solving for, plus 25.232. Keep in mind, it's super common to end up with decimals. Anytime you're dealing with any kind of linear regression, you're probably going to end up with answers that are ugly, which is why I was so surprised when I wrote my own equation I had nice whole numbers. I'm going to subtract 25.232 from each side. 49.768 equals 3.2911x. I'm going to divide that by 3.2911, and I get 15.121 equals x. So the question says, estimate the cricket chirps when the temperature is 75 degrees. I would estimate the cricket chirps to be about 15. B, estimate the temperature. So now I'm solving for Y when cricket chirps is 18 times per minute. So I would then use my same model. I would solve for Y. I would plug in X of 18. And then just do the math just like I did before. So 3.2911 times 18 is 59.2398. I'm going to add 25.232 to that, and I get Y equals 84.4718. So my temperature would be about 84.5 degrees Fahrenheit. Last one is for you to try, and again, I really do encourage you when I give you time to do these to actually press pause and try the question yourself and then press play to see how you did. When I created my equation, I used the graphing calculator capabilities, so if you do that, you should get the exact same equation as me. Press pause, try the question, press play to see how you did. So again, I'm not going to show you the whole equation or anything and how I came about it because I went through that in detail before, but this is the equation that Desmos came up with for this particular XY set. And remember that Y is class averages and X is absences. And so that's important moving forward because in B it says use the model to approximate the average. So I'm solving for Y for a student who misses 6 classes, that's X absences. So that tells me which one to plug it in for. Y equals negative 3.27 times 6 plus 98.145 before I do the math there, just keep in mind why that slope would be negative. Keep in mind that as absences increase, we would expect a student's approximate average to decrease because they're missing out on all of that content. So it makes sense that I have a negative slope here. This gives me negative 19.62, and I'm then going to add 98.145 and end up, 98.145 and end up with 78.525. So the answer to my question is I would expect a student who misses 6 classes to have an average in the class of 78.525.